The stress concentration effects. Number of times we have geometric discontinuities such as the holes or sharp fillet radii or keyway. These are probably the most prevalent cause of the failure because of the hole, keyway or the sharp fillet radii at local there is a stress is maximum than as compared to the rest of the given machine element. So to explain the concept of stress concentration, let's consider we have a flat bar of width equal to W and a uniform thickness equal to H. So if you take any section at any distance from the left hand side, you will find that it has a uniform cross section, and this cross section is perpendicular to the force F. So this cross section is always perpendicular everywhere, and the cross section is given as the width multiplied by thickness equal to H. So this arrow represent here the stress, and this stress is called as the nominal stress, which is simply equal to force upon area. So whenever we have a bar and is subjected to the external force F, then we have uniform stress across the section, and this stress is represented by the arrow length is equal everywhere over the section. So consider here a plate where we have made a hole in the same plate for any purpose, either for passing the bolt or rivet, and let the diameter of the hole equal to D. So this section here is AA section, and for this section we have the stress is equal to force upon area, and this section has the area equal to width equal to W and the height equal to H. So correspondingly we have a stress that will be equal to sigma is force upon area. Since here the area is maximum, so corresponding stress produced will be the minimum stress, so we'll call this one as minimum stress. But if you consider the area at the section, that is this section here, now this section we can represent, that is we have a hole here. So this section I am showing you separately here. So at the given section, this hatch area represent the resisting area, and the total hatch area here will be equal to, let's call it A1 is equal to we have width minus the diameter of the hole multiplied by thickness equal to H. Correspondingly, the stress produced at this section will be called as nominal stress. It is represented by sigma nominal and is given as force upon the area A1. This stress I can represent is this way. But if you approach exactly at the top edge, that is this point here, and at this point, that is the local points here, we will find here that is a sudden rise in the stress. So this sudden rise of a stress is due to the stress concentration, and in this case we have maximum normal stress is produced at the top and at the bottom, but this stress is produced at the local points here, and this maximum stress we can find out using the stress concentration factor. What is exactly the stress concentration factor? That we can justify by using the fluid analogy. For this one you have to consider a uniform cross section pipe, and the streamlines are parallel to the direction of flow. So we will find here the streamlines are exactly parallel to the direction of force. So this one is representation of a streamlines. And since there is no disturbance in the flow, the streamlines will be exactly parallel to flow, and you will find here there is no concentration of a streamline at any local point. So we can very well apply the streamline analogy in a channel when the flow to the force flow lines of a flat plate without any type of flow subjected to uniform uniaxial tensile stress, and the corresponding value will represent here as the stress which is given by this equation. So this is a uniform stress over the entire cross section, and this value is same as sigma is equal to force upon area, and this time we have area is same as equal to this area, which is equal to width multiplied by H. So these are representing here the stresses, and all the stresses here as equal in magnitude. Now consider the second situation in which we have a hole and the plate is subjected to external force is equal to F. So this plate is subjected to external force equal to F. Now there is an obstruction here. You can imagine this obstruction may be a stone or a boulder in a flow path. Up to this section there is no obstruction, and after the hole there is no obstruction, so streamlines will be parallel. So in this case we will get a streamlines will be parallel like this one. So these are the few streamlines I am showing you. Again afterwards we will find here the streamlines are parallel because there is no obstruction to the flow. What exactly happened near the hole? So this streamline will continue as it is. This streamline will try to divert in this fashion. Remember, this is a freehand drawing. This streamline will go to pass like this one. And if we have another streamline, it will go near the hole and will then bypass. So our observation here is that the streamline is get concentrated over this section. So at this section here, we'll find here there is a concentration of the streamlines. So whenever we have any type of geometry irregularity like hole or the sharp fillet radii or the key, in that case, or even you can say the notches also, effectively it increases the nominal or theoretical stress as we move closer and closer to the theoretical stress. And there is a concentration of a stress at a location where the stress concentration is present, and therefore we have maximum stress is produced where we have the stress concentration. So at this point we have a stress concentration, correspondingly we have maximum stress is produced at the local edge. So if there is any obstruction such as a heavy iron ball or a pipe or a stone boulder in the path of flow water, the flow water or the fluid flow will not be smooth and straight as shown in the previous figure, but they have concentration of a streamlines at the obstruction. So because of a geometrical discontinuity, there is a sudden increase in the stress, and that is called as the stress concentration. So at this local point we have stress is maximum, that is given as sigma max. We can calculate this sigma max from the nominal value using the stress concentration factor, and then the stress will go on decreasing as you approaches towards the edges. At this time we have to show the stress here, so which one is basically the nominal stress. So nothing is given here. In that case you have to select the value of the stress which I have shown externally here, which one is same as called as nominal stress, and this nominal stress is given as force divided by area at this cross section, which is W minus D. That is the width of the plate minus the diameter of the hole multiplied by thickness H. And this value of sigma max we can calculate using the theoretical stress concentration factor. Since here the plate is subjected to the normal stress, so we'll define the theoretical stress concentration factor for the normal stress, and it is represented by K suffix sigma. And it is a ratio of the maximum stress sigma max divided by the nominal stress. Now remember the procedure to calculate the nominal stress. Nominal stress is that stress where we have a minimum cross section, and the stress where we are taking the total area, that will be the minimum stress. So minimum stress is different, nominal stress is different, and the maximum stress is different. This maximum stress will occur only at the local point here, which is the top edge and the bottom edge. So sigma max represent here the maximum normal stress, which one is megapascal, and sigma nominal represent here the nominal normal stress. It can be computed as F by A, or it can be computed by the bending, that is a flexure formula, which one is bending moment multiplied by Y divided by I. So this elementary formula you can take to calculate the normal stress, and this value of K sigma is called as theoretical stress concentration factor for a normal stress. Similarly, we can define the theoretical stress concentration factor for the shear stress also. So theoretical stress concentration factor for the shear stress will be represented as K tau, and it is given as a ratio of the maximum shear stress, that is the value of tau maximum divided by the shear stress nominal. So we have nominal shear stress, which one is computed from the torsion formula, that is we have T divided by J multiplied by R. So if you are using a torsion, then you have to use the theoretical stress concentration factor. If you have a axial loading or a bending, in that case we can use the theoretical stress concentration factor for normal stress, which is represented by K suffix sigma, and this is represented as K sub tau. So whenever you have to design a machine part, you have to take care of sigma max. That is, you must consider the stress concentration occurring in such part and eliminate or reduce the stress concentration. Now this graph is available for calculating the value of the stress concentration factor K sigma, which is given as sigma max divided by sigma normal. So on the y-axis we are plotting the stress concentration factor K sigma. On the x-axis we have a ratio of the diameter of the hole to width of the plate. This figure is shown here. We have a hole here of diameter equal to d and width equal to w. So we can very well calculate the stress concentration factor using the known value of diameter, that is a hole diameter, and the width of the plate. You have to just locate that value. Suppose we have d by w is equal to 0.3, then you have to locate the point on the graph, and correspondingly you can record the value of the stress concentration factor, which one is very close to 2.4. And using this stress concentration factor, we can calculate the local maximum stress, and this maximum stress must be less than the yielding, then the part will be safe. Otherwise there is a chance of yielding at the localized point. So you have to take care here is that the value of sigma max must be less than equal to SYT. If this is so, there is no yielding, and if there is no yielding, the part will not fail. So this one is designing the safe working. So part will be safe. Number of author uses the symbol for K sigma as K sub T. T for theoretical stress concentration factor. And theoretical stress concentration factor for shear stress, they will denote as K sub T S. S for shear, T for theoretical, K for stress concentration factor. So either we can use K sigma or KT. KT for normal stress and KTS is for shear stress. We can record the value of KT and KTS. So various graphs are available in the data book. So any type of geometrical discontinuity in a part, then there is a chance of stress concentration. This geometry discontinuity give rise to the stress concentration, and since we have the stress part, a higher chance of failure. That is the value of sigma mass as local light point may exceed the value of SYT. This one is a very bad thing about the geometry discontinuity or the stress concentration, but you cannot avoid it. Then you have to design against this stress concentration, that is considering the value of theoretical stress concentration. You have to design your part. But in the case of ductile material, the value of the stress concentration does not make any significant effect, and therefore the theoretical stress concentration factor is normally neglected in the case of ductile material. But as far as the brittle material is there, we have to consider the stress concentration factor. Suppose for certain dimension you get the value of nominal stress sigma nominal is equal to 120 megapascal, and we have d by w as we have taken here is equal to 0.3. So if we have d by w is equal to 0.3, in that case we have kt is close to 2.4, I will say 2.35. So if you know the value of kt, then we can calculate the value of sigma max, which is same as a theoretical stress concentration factor kt multiplied by sigma nominal. And since we have kt is equal to 2.35 and we have sigma nominal is equal to 120, so the maximum stress is produced at the local point at the top and bottom of the hole will be 282 megapascal. And suppose we are given the value of SYT is equal to 260 megapascal. Then what we conclude here that this value is greater than SYT, so there is a failure. So the designer must consider the value of sigma max. So this figure indicate here that we have a flat bar and we have made the hole here. Because of a stress concentration at a local point here, there is a fracture is developed. So you have to avoid this fracture. This is called as local yielding. At here we have local yielding because the value is exceed than the value of SYT. So the stress concentration can be reduced. If we have a circular hole, what you have to do is that we have to make here two smaller size of the holes nearer to the larger size of the hole. Because of this, we'll find here the stress concentration will going to decrease. This is true in the case of static loading. You can very easily compare the two figures. This figure we have a single hole and there is a lot of stress concentration near the edges. But if you make here two additional holes, then there is a smoothing of the lines. Initially it's a very sharp abrupt changes of a flow stream lines, and therefore there is a higher value of stress concentration. We can reduce this stress concentration by providing some geometric changes of a force flow lines, which will get to smoothen. But if you have a case of fatigue loading, that is in the case when the load F will changes with respect to time, it will be a tension and then it will be compression. Again it will come in tension and then in compression. This type of loading is called as fatigue loading, and in case of fatigue loading, the fatigue strength of the part with the stress concentration of the stress razor can be increased by cold working operation. Cold working you can perform by using the short finning or pressing by balls, which create a nature of a stress in thin layers of the part just opposite to one induced in it. That is what called as the cold working. So you can improve the fatigue strength by using the cold working. So theoretical stress concentration factor in the case of normal stress, which is represented by Kt, is sigma maximum by nominal stress, and theoretical stress concentration factor for shear stress is represented by K sub Ts is tau max by tau nominal. These two values you can neglect in the case of ductile material and in the case of static loading. So in the case of ductile material, and that too in the static loading, we normally do not consider the value of Kt, that is a theoretical stress concentration factor for both, that is the normal stress as well as shear stress. And for brittle material, the static loading, we use the value of Kt and Kts. The reason is the stress strain diagram for the ductile material and the brittle material. Now we are familiar here with the stress strain curve for ductile material. So we'll plot the value of sigma versus strain. So initially we have a direct relation between the stress and strain, and they are increasing linearly. Then we have upper yield point after 0.2% offset, and then we have the plastic deformation up to SUT, and then we have fracture at this point. Whereas in the case of brittle material, if we have a stress versus strain, then the ductility part is not present in the case of brittle material, and the value will be of SYT is same as equal to SUT. So we have a failure at this point. And in the case of brittle material, what we observed is that the value of SYT is almost same is equal to SUT, and ductility part is totally 0. This point is representing here the value of SYT, and the value of SYT is much lower as compared to the value of SUT. So yielding is represented by different point in the case of ductile and the brittle material. So when we say the maximum stress will increase and it will come into the plastic part, then there is some permanent strain is produced. So as we have discussed in the hole in a plate, there is a stress razor here, that is a stress concentration or the stress razor points. And this concentration of a stress is taking place at point. So this one is called as local stress concentration. It is not over the entire part, only at the top and bottom we have a stress razor. And if this value of sigma max here will be lower than the value of SYT, so if we have sigma max is less than SYT, then there is no yielding. So this point here represents the yielding. Once with the part will yield, suppose the value of sigma max will be more than SYT, then it will start yielding, and this portion is a non-linear portion. So when the material yield locally, its stress strain curve become non-linear and of a low slope, which prevent a further significant increase in a stress at that point. As the load will increase, that is the value of F will increase, more material will be yielded, bringing more of the cross section to that stress. So more area has a maximum value than the value of SYT. Now because of local yielding here, that is at this cross section, we may exceed the stress beyond the yield, but while the remaining cross section here entirely has a stress is sigma norm and the value of sigma norm is less than SYT, then we say that the part will not fail. It's a locally yielding. See, this local yielding I have shown you in the last figure. So here you observe the local yielding. So this part is yielded, but the part will not fail. That is the idea. In the case of ductile material, the value of KT and KTS is normally not considered. So thus it is a common to ignore the effect of geometric stress concentration factors in the ductile material under the case of static loading. But when we have a fatigue loading, then you have to consider the geometrical stress concentration factor. It really matters that where the maximum stress is produced. If the maximum stress is produced locally, then we'll say that there is a local yielding, and over the entire cross section we have a stress equal to sigma nominal, which one is much less than SYT, so yielding will not be there and the part is safe. As far as a brittle material is considered, the plastic part which one is present in a ductile is totally not present. So this part is not present, and therefore if you have a local yielding, then it will exceed the value of SUT. So suppose we have sigma max value will exceed the value of SUT. So there is no local yielding because you can't exceed more than SUT. In that case we have a failure. So plastic region is not present in the case of brittle material, and therefore the failure is always there. So because of a failure is occur due to the stress concentration, so the value of KT and KS must be considered in the case of brittle material. So brittle material will not yield locally since do not have a plastic range. Thus the stress concentration do have an effect on their behavior even under the static load. Once the stress at the stress razor exceeds the fracture strength, a crack begins to form. This reduces the material available to resist the load and also increases the stress concentration in the narrow crack. The part then goes quickly to failure. So for brittle material under the static load, the stress concentration factor should be applied to increase the apparent maximum stress. So you must consider the stress concentration factor for brittle material. That is the value of KT as well as KTS in the case of static loading must be considered in the case of brittle material. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.